Are you ready to start?
Yes, I'm ready.
Okay, so I go to introduce you. So the last speaker of today of the workshop is Marius Junge from University of Illinois. Poisson, Poissonization, boundary, and relative entropy. Please, thank you.
Okay, first of all, thanks for letting me speak in this, workshop, which is a very, very interesting, almost a very interesting circle. That's what I've observed in the 2 days I was trying to join you. And also thanks for adapting the times in a way where this can be done from Europe and the US. And appreciate this. 7 o'clock is a little bit hard, but anyway. So I will talk. This is joint work with a student from physics, Yidong Sheng, here at the University of Illinois. And so I have to admit that I'm probably trying to do something which you have already done, right? I mean, find a good model where you have field theory, relative entry, and boundary combined at the same time. In the previous talk, we talked, it was talked about how to take the limit. That limit action has to do with boundary, at least in my point of view. So I will start there. So this is exactly my goal, to combine boundary area formula or some relative entropy formula in field theory. This is written in small letters because this is still the hardest where, at the moment we have certain things, but we are not totally happy with everything. This is really work in progress. So we started like 1.5 years ago. So there's a little bit more work to be done. And so let's start with one of these formulas, which probably most of you have seen and which is still mysterious to me, right? So somehow there is, in this overview paper of Witten, there is a formula where you calculate the exponential of a certain differential form in the boundary and write it as the exponential of a smeared out operator in the CFT, right, with respect to a state in CFT, right? So that is an extremely interesting formula, except that I don't really know how to do that. But I mean, this is certainly a motivation I want to look at. Now, I also have to say I'm more, mathematician than physicist. For me, the formulas are the motivation, and that not the other way around. That's just the way how we tick, right? I mean, you cannot change that. So now let me talk a little bit about boundaries. Boundaries have many meanings, and I want to start with the first one, of course, which is the one we all know. You take a circle, you have a function here on the disk, and you send the function to the limit, right? So they often take these radial limits, and there's a lot of harmonic analysis. You can maybe also go from here, but you shouldn't do a tangential limit. So if you have a function on the disk, you can restrict it to the circle, and that is certainly one operation, right? So we have a map which, right? So we take the limit, and so for a function on a disk, you can take the limit. Now, there's an inverse operation, which we all know, I mean, Poisson formula. So if you have a function given on the boundary, right? So if your function is given on the boundary of the disk, which is S1, here's your function, then you can extend it to a function onto the interior. But you realize that this extension doesn't give you an arbitrary function, it gives you a harmonic function. So there exists a function h, so that the h restricted to the boundary of the domain is f, and delta of h is 0, right? So that makes these functions harmonic, right? That's the definition of harmonic. So let me look at this from an operator. I will write down the formula for this in the next slide. So if you don't believe me, wait a second. But I want to mention what happens here from the point of view. We have the bounded function on the circle. We have harmonic functions on the disk, and then they sit, of course, in bounded functions on the disk. Now, I wrote here h infinity because you don't have to assume that these functions are continuous. You can do this even for measurable functions, and that's the language of von Neumann algebra, so this is why they got these interesting letters, right? So this is probably one of the easiest boundary procedures we understand. And here is this Poisson kernel, which gives you the harmonic extension, right? So this is the harmonic extension. If the harmonic extension, if you look at the formula here, thanks to the theta minus t, if you want to know somehow, if you calculate, here's your function on the boundary, if you calculate this value, you all know this has to do with Brownian motion. You really have to know all the values on all the boundary points in order to get this value. And this procedure in principle is very non-local, right? I mean, if you're close to the boundary, still all the other parts of the boundary have a huge impact, not a tremendous impact, but some significant impact to the function, you know, which so this formula really requires knowledge of the whole function on the boundary. That's just a comment. Okay, so this is probably in hyperbolic geometry, this would be different. If you change the metric, then somehow the function close to the boundary really only depends on these values. That would be a local picture, but that is not, you know, this Poisson kernel does not correspond, right, to this formula. I mean, this corresponds to that formula. So this would be a hyperbolic picture. And that is, you know, more, you know, standard Euclidean picture. Good. So there actually has been a lot of attempts to now I don't see, oh, here it is. So it has changed. There are a lot of attempts to actually understand what is a boundary in terms of operator algebras, because, you know, if you do not, you know, think about non-commutative geometry, you do operator algebras. What is a boundary? You cannot talk about points, and so you have to be careful. So I think this started by an idea of Kohn. That's what I learned from Peterson. Then it was, you know, extended by many people, and I'm definitely forgetting here 5 or 6, which are important. So, you know, the idea is to start with a completely positive map on a von Neumann algebra, unital completely positive, and then look at the fixed point algebra of that map. And this fixed point algebra is a subspace, right? So this is a subspace of the algebra, but not the subalgebra. Like our harmonic functions before, they are a subspace of all bounded operators, but they're not everything. And they're a priori not closed under products, right? So this is important that this here is a subspace, not a subalgebra. Right? That's the feature of these guys. But this subspace is nice because if at least the map phi is normal, one can define a projection back on that space. And this is the typical ergodic average, right? You define a projection using these ergodic averages. And then you find an inclusion map, right? This subspace here sits in the von Neumann algebra. And then you project back onto this space. And this situation is known in C-star algebras for a long time. It simply says that, well, you know, you can now define a product on that subspace and think of it as a von Neumann algebra or a C-star algebra. And that would correspond to thinking of the bounded functions on the boundary as an algebra, which are somehow obtained from the data on the whole space M. Yeah, so this is I think I wrote this down. Yeah, this is the Choi-Evras product, right? So you define the new product at x times y, you project the product back. And then you have to actually really, you know, this is one of the few points where you check the axioms of a C-star algebra word by word. And abstractly, this is a C-star algebra. It's a very cute argument. And so this gives you this famous Choi-Evras product, which is a non-commutative model for what happens between harmonic functions, boundary functions on the circle, and the whole disk. So abstractly, we could call a boundary whenever this situation occurs. So if we have X contained in M's with some kind of order embedding, right? We want to actually probably consider order, and then we have a projection back to X. In some cases, you have to take some kind of closure, and I don't want to be very specific about this. This depends on the situation, right? So if the map phi is normal and then you can work with the weak star closed space, it works. If it's not normal, then one has to maybe go to the double dual if necessary, right? So so we have a factorization from X to X double star through this M. And that's a version of an operator algebraic boundary. By the way, boundary, even if you translate from groups to von Neumann algebras, one has to be super careful because sometimes they are talking about the von Neumann algebra, sometimes about the C-star algebra, and depending on which category you use that, the notion of boundary changes its meaning. So it's unfortunately, it's a very powerful concept. Poisson boundaries have been used in operator algebras very successfully, but they are also always a little bit, you know, tweaked for the convenience of the application. So one has to be careful there. Okay, yeah, there are other boundaries in CFT. I've seen often forms of boundaries by these light cones, right, of that form. This is not what I'm doing right now. Maybe this will fit in this project later, but at the moment, I'm not doing this. I'm just really talking about this operator algebraic boundary. So just as a warning, if I talk boundary, this is not the one I mean here. I mean really this operator algebraic viewpoint. Good. There is a lot of theory about this. Here we go. And this is the work by Kirchberg. I mean, probably have heard about the Kohn embedding problem and the negative solution, which is based on Kirchberg's work. But one of the things he did in his work, he actually started with the von Neumann algebra M. And then he asked, when can it happen that we have a map from M to X, which is a quotient map, right? Quotient map means it sends the open ball to the open unit ball. Actually, he wants even to send the closed unit ball to the closed unit ball. Right, he really wants that one. This is the one he's studying, and then he showed that this happens if and only if, right? So if you dualize this picture, you see that you can embed X star into M star, right? I mean, a quotient map, the dual is an injection, and then he studied when that happens, and he showed that this only happens in a very algebraic situation. Yeah. So this is his work, but it was instrumental in proving some of the equivalence of Kohn embedding projecture with the C star formulation. So it's important in that context. It's just a good thing which I want to remind you because we will use it in the next page, right? So I just write down the dual picture, assume that M star is separable, and we have exactly this situation that I have another map from a pre-dual of a von Neumann algebra into a pre-dual of another von Neumann algebra, which happens to be separable. And the map is two isometric. So this means if I extend it to 2x2 matrices, it's also norm-preserving, right? So that's a little bit more than what Kirchberg wants to do, but he can reduce it to this case. And then this is the case if and only if there is the conditional subalgebra of M, a map from N to this conditional subalgebra, right? So N is isomorphic to some N tilde contained in M. And if I mean conditional, I mean that there's a conditional expectation from the algebra back to N. And this conditional expectation is used to actually define the isometry. So the isometry has this very nice form. If you apply, you take some faithful normal state, phi n, on the subalgebra, you multiply it in the Takizaki way, right, with an operator. This is the same of pi of x times phi of m. And of course, phi m is really the conditional expectation, phi n composed with the conditional expectation. So these isometries appear only in a very, very special algebraic form. That's what Kirchberg's theory, which was proved for a different purpose, just implies in this situation. And that means abstractly that every abstract boundary, the double dual is isomorphic to an algebra of n double star, right? So X is isomorphic to some, and that isomorphism, which goes to the double dual, if your inclusion maps are not normal, think about these limits you were taking in the previous talk, right? These limits are often not normal. They are taken in a very special way. So if you ignore some of the limit procedures, you can put it in a double dual, and then this mapping becomes an algebra homomorphism. A little bit surprising, but that's what Kirchberg's theorem simply implies. Okay, so this is about boundary. This has a nice connection to recovery, which we also heard about in this conference. So let me remind you of the definition of relative entropy, which at this point of the conference is probably ridiculous because you have seen it only 5 times. I also want to, okay, very interesting. Yes. So maybe I should try this one. Yes. 1, 2, 3, 4, 5. I got a spam call and this changed my picture. So here I defined the relative entropy, and for a map from one pre-dual of an algebra to another one, which is trace preserving and completely positive, I can then look at the difference of the relative entropy. So the relative data processing and quality says that this difference is always positive, but what happens if it's 0, which is a well-known case by Pett's theory, actually. And what we say is this is the case if and only if, right? So I have a map from M star to M hat star, this happens only if I have a subalgebra and a map from n lower star to n upper lower star. And what happens here is that n is contained in M, and n hat is contained in M hat, and both of them are conditioned, right? So if they're conditioned, then the pre-duals are comparable. I mean, the pre-dual embeds isometrically in the pre-dual of the other. So relative entropy difference is 0 if and only if we are in the Kirchberg situation, right? So if and only if the maps are actually given by complete isometries, right? Now, I should tell you that this is very local, right? So this construction depends on sigma, as it should, right? I mean, so if we fix sigma, and then these maps, they depend on, so the isometry which you construct here depends on sigma. It's not universal, it just depends on the soil. And also this equality being 0 is used in this construction. And that unfortunately means that we don't really know what happens if this entropy difference is only very small. Then I'm not able to prove at this moment that there's an almost isometric embedding that is open, right? So exact recovery only happens in the isometric embedding situation, right? So if you have an isometric embedding, it's not very surprising that this means that entropy is preserved, right? I mean, you just look at the definition.
Sorry,
yeah.
A small question about that last statement. Do we know what it would mean to have an almost complete isometry?
Well, you could somehow say there is a CB perturbation of it, right? I mean, it's CB close, and CB close means for maps between p-duals, you have a notion of, in quantum information, they call it the diamond norm, but there is a version of the completely bounded norm, and if the difference of two maps in CB norm is small, then that would be a perturbation of a complete isometry. Or you could just ask that the map here is not completely isometric, but completely isometric up to an epsilon, right? So the norms are not equal, but the norm is bigger than 1 minus epsilon and smaller than 1 plus epsilon. So yeah, unfortunately, we have many ways to define what it means to be almost isometric, just no way to prove it.
Okay, thank you.
Yeah. So defining it in this case, because we are doing the pre-dual norm, then the norm is, and you would probably extend it to matrix algebras to all levels in order to have, relative entropy and action with environment preserved. Okay, so that's one connection. I want to mention another connection to, after we have this relative entropy. So there's one famous error correction example by Hollow. He starts with a dimension H. His dimension is, his space is 3-dimensional, and all of these guys are also 3-dimensional, but one can easily generalize this to a higher dimension. So he calls this a code subspace, and we are looking at, our von Neumann algebra N here is the bounded operators on A1 tensor A2, A3, right? So finite dimensional algebra. And this, and we have here the subspace. So this, of course, contains the bounded operators on H. And so there you have natural boundary maps. So what, these people imagine, and I think this is a pretty correct picture, is that the boundary maps are just given by partial traces, right? So we partial trace out. I wrote the L1 notation because the partial traces are maps on the pre-dual, so that we fit this pre-dual picture, which I used the page before. And in von Neumann algebras, you have to distinguish between the algebra and the pre-dual much more. So these are really maps from this, from the L1 space of B of A1 tensor A2 H3, which is nothing else but the Schatten class, right? So, and we just trace out one out of two component, and then this is the L1 space of the one component. And what happens is, what he proves, or he characterizes, is when does it happen that for all rho and sigma in the bounded operators of the code space. So it's not true universally, right? So this equation here is true in all cases, but you only for very special densities. I mean, we had some discussion, for which states do you expect certain equalities to hold? Well, often they have to be very special in this coding procedure. Rho and sigma have to be densities given by the code subspace. And for them, it happens that the relative entropy is equal in all three components. And that simply means by this recovery picture that you have to be able to lift. If you know the information on one of the slides, you can recover the information on the Hilbert space H. And this recovery maps exactly recovers the information from every boundary back to the space, right? So if this relative entropy holds, then this has to be true. Yeah. So this is another version of thinking of boundary. If you can recover your data from the boundary, then you must actually have an isomorphism in some sense from the yeah. I mean, either from the boundary to the bulk or the other way around. I mean, depending on what your assumptions is. Here you must recover the code space from the boundary in this picture. Okay, so this is another interpretation of boundary. How am I doing on time? Yeah, I have some more results on recovery maps. I think you heard of them before. So let me just make two comments. So we also proved, actually we followed the proof by Wild and our paper to prove a recovery result. So this is always about studying almost identity in this relative entropy inequalities. Let me just make two comments. First of all, we do not actually prove the same result as Faulkner and Holland do. We prove a different result. We use the same ideas. We prove a different result with a different, test function. And the test function here is this P and P fidelity instead of relative entropy, what they prove. That being said, that's kind of fine. But the important thing which I want to mention is these results allow you to prove something interesting. Namely, if you have two states if you have two states in the GNS reconstruction which represent two states, right? If you're in a von Neumann algebra, you have always GNS vectors in the corresponding L2 space. So what this says is that if the relative entropy under a channel map is not changed too much, then you can not only recover the state, you can recover the GNS vector of that state, which I think it's a cool interpretation, right? So the right way to recover is to recover the GNS vectors from the states. Yeah, so that can be helpful. And there are some calculations, so this is why there's a constant popping up. Okay, so that's about recovery. And now I will come to the central part of my talk, which is this Poisson process, which is classically super simple. I mean, I think many of you have seen that if you give yourself a measure space, and then you can construct a family of random variables for every subset of in sigma, right? And these are Poisson random variables with a probability, so discrete random variables with a probability to have n points is given by this formula here. And mu is called control measure, right? So this is the notation they use, control measure. Okay. And then, of course, it has these properties abstractly. If you take certain regions, right? Here's your omega, you have one region. If you take all the characteristic functions which live in here, and then you look at the algebra A of omega 1, right? The algebra A of omega 1 of all these random variables indexed by these different sets, but they are contained in here, then if omega 1 is contained in omega 2, or A1 is contained in A2, then the algebras are contained in each other simply because you have more random variables. And simultaneously, if they are disjoint, then these algebras become independent. So this is something which, in some sense, if you think of if you look at these tensor models, that's exactly what you see. You want to see that different regions actually split up into different tensor products. So this Poisson process, this commutative one, has that property. It's just too commutative, right? But it has this independence property, and it can easily be generalized to a non-commutative Poisson process. So it's easily, so this is a little bit of a K-FET here. Many results here, which I've done some years ago, they work for semi-finite von Neumann algebras. And if you want to extend them, one has to work harder. But let me stick to the semi-finite case for illustration. So here you start with a von Neumann algebra with a trace. and then you construct another algebra, the Poisson algebra of this guy, and a map from good elements. So these are elements which are bounded and have finite trace norm. And you construct a map so that if you look at the algebras generated by E and E, so E is a projection which is finite. So then these are random variables, right? So they're just non-commutative elements in this L0 space. So if the projection is smaller, then the operator algebra is also smaller, right? So they have this isotonic property, which we're looking for. If the two projections are orthogonal, then the corresponding maps here commute, right? So it has this field aspect, right? I mean, it's not the full Kastler-Haag field axioms for quantum field theory, but it has at least this isotony and the commutation relation. So these axioms here, they're kind of natural for the Poisson process. And then also there's something nice, namely, if you start with a trace, what you get here at the end is another trace, but this is a finite trace. And you can calculate, you can calculate the trace of e to the lambda x is trace of e of x minus 1, right? So this is this Poisson formula, which comes from the process. And yeah, I mean, I give this talk because this reminded me a lot of this Witten formula, right? The trace of e to the lambda x is e to the trace of e of x minus 1. So this is kind of, in some sense, we will see that this is in some sense an area formula built in. Okay, I think that's exactly what I'm doing now. No, the next thing is, so here I did this for traces, right? So that's something I knew probably like 10 years ago. And then with Chen, we tried to extend this to weights. And the result we get is that you can extend this Poisson process to weights, where now the formula which we are expecting is something like phi weight of e to the lambda of x should be e to the weight of e to the x minus 1. So this is the formula we want for the weight. So that's what we have in mind. But what happens is the following. So we start with a weight, and we assume that we have a Lie group in the unitary group of the von Neumann algebra. And what we can do is we can construct this Poisson algebra, which still has the strongly continuous action of that Lie group, right? And it has this canonical formula. So on these generating elements, it somehow behaves exactly like that it should, right? I mean, it conjugates. It's kind of a the Poisson map commutes with the group representation, right? That's what this is saying here. And then this extends to an automorphism, and so that's okay. Yeah. So we have this extension to weights, and this extension to weights preserves certain group actions. Universally, we don't know whether this always leads to strongly continuous a map from the unitary group of the original von Neumann algebra. We don't know whether we always will get a map from there to the automorphism group of the Poisson algebra. But for Lie algebras, this actually works, right? So for nice subspace, not subalgebras, it works. So now we have this Poisson algebra for weights, which will allow us actually to do something very fancy. So let me just do, one motivation. You start with a Lie group. And this acts on some Hilbert space, P of H. Yeah. So, and then you could actually look for, you can look for one of these you take an element in the Lie algebra, and you look at the image under one parameter group. Now this here is necessarily of the form ITEA for some A, unbounded operator, but self-adjoint on H. And the weight we want to work with is e to the A. Why? Because then W to the IT X W right? So if we use that weight, the corresponding state which we obtain, they will, so this is on the Poisson algebra, this is on the original algebra, but they will have the same modular group. And once we have the same modular group, then we can try to apply standard subfactor theory. If we control the modular group, this is always a good start. So this construction works, right? I mean, so we can do that by simply, you know, for instance, if we equip here this with a trace, then if you assume this group action to be trace preserving, then this will give us a nice. So on this new Poisson algebra now, which depends on the weight, which is no longer the same if we do it with the trace. So this is a new object. That's fine. Yeah. Good. So this is where we have a hope to apply this to field theory and construct fields. So the main idea in these constructions is very simple. You simply take a limit of finite pieces, and for finite pieces, it's just a direct sum of symmetric tensor products. So we have a concrete way to calculate certain things. There are nice formulas which work for relative entropy. So if you have a certain random variable x in your original space, right? So a nice random variable, then e to the x, of course, will be positive. And what you can prove, and I think this is partially known in some special cases, I've seen this in papers of Longo. So the relative entropy of this normalized, you know, so this would be a normalized state, right? So this is the relative entropy of phi x, phi y is exactly the Lindblad entropy of Ex and Ey, and the Lindblad entropy is this linear correction term. This is simply because these guys are not normalized, right? So they're non-normalized. E to the x, e to the y, they are not normalized. For non-normalized states, you have to do this. So Poisson process already produces these kind of automatic translation of calculating the relative entropy for certain states by calculating the Lindblad entropy for their symbols, right? And I think these kind of similar formulas have been used extensively in the work of Longo to actually calculate specific relative entropies with respect to a reference state. Yeah, so this is the general feature which holds for all of these Poisson processes whenever they occur. Good. So for instance, if you take formally, if you have a projection, you can formally take ln f. Well, it's not very finite, but you know, this exponential lambda of ln f makes actually sense. So what we get here is the relative entropy of these new states if you have two projections, f1 less than f2, then phi of f1 is a state which corresponds, which is a quantized projection. And then the relative entropy of phi of f1, f2 is just a trace of f2 minus f1. So this is an area formula without entropy, simply because the states are very special. Right? They're projections. Yeah. So I hope that these are formulas which are in some sense familiar. I think this can be extended in some situations where we replace the trace by the weight, but let me not insist on that. Good. So we have these features all together. There is some nice combinatorics of these Poisson process, which goes over all partition functions. So for arbitrary variables, it's not just 2-point functions. We really have to take multiple point functions. That's a feature I want to mention for those who actually can do something with it. Also, what we can prove is that if we have a boundary situation, so we go from x contained in M, so this is some kind of boundary bulk back to X. If the weight is actually chosen here and then extended to weight here, then the Poisson algebra and the boundary are compatible. So this means once we can construct a good quantum field theory on the boundary, then we can also extend it to a quantum field theory on the bulk, on the Poissonification of the bulk, which gives us a lot of non-commutative fields. And so that's actually what we are trying to do. We try to understand a good quantum field theory on the boundary for certain particular operators, right? So this is this picture. I think I just reformulated here, right? So the bulk boundary, the boundary to bulk to boundary inclusions translate in the Poisson the functor somehow preserves that, but one has to be very careful about which weight to choose, right? So it's not a freebie, one has to be very careful. And this weight here exactly corresponds to taking very particular limits towards the boundary. So this is the delicate part to make sure that this here still has meaning. Okay. Now, right, so in a canonical example, we can do this, for instance, with the circle and the boundary. So if you apply this to the circle and the boundary, we would get, then we would take here the Haar measure on the circle. And then you have many choices to choose W here. The way, yeah, so that is, again, that is kind of the delicate part. In the limit, you would really take something which is supported as closely as to the boundary as you can. So you should think of this as taking a limit towards the boundary and then take these rings. This is the most appropriate interpretation for what happens for the weight here. Right, and then since we're going to the end of the talk, I think I mentioned this Lie group example already. So this is a good example. And then we tried this we tried this for the bounded operators on L2 of S1, and we take here the SL2R action, right? So this acts here, and then you have to maybe we try to find look at a certain Poissonization, and then we want to have here a family of algebras AI indexed by the regions. So this is what we are working on these days to find this nice quantum field. I mean, it's not a freebie. I mean, the while operators have a good property that they commute if the imaginary parts vanish, but this here is a little bit more rigid because we're going from 2-point function to multi-point functions. So that's where things are a little bit more difficult. So this is what we are working on, right? So this is our goal for the next couple of months, I guess. So let me start with the conclusion. So Poissonization is compatible with boundary procedure and suitable weights. It has this orthogonality, orthogonal to independent property. It produces some kind of natural volume formulas for relative entropy. And just for your information, if you look at this formula here, it also tells you can only do this for relatively small perturbations, right? F2 minus F1 has to be trace class. So it's not for large perturbations, it doesn't work because this number here often will be infinite, and that is a model case. So that's what I wanted to say there. Yeah. So yeah, and then we conjecture that we actually can construct some kind of quantum field theory using this Poisson algebra on the circle, which is compatible with the dilation group. So that's what we are trying to do. And this, you can think of this as a slight extension of the Weil algebra, where we allow some extra, what they call in quantum probability, gauge operators to be in the algebra, right? So it's the Weil algebra plus a little bit more. And that's what we want to realize here. And I think it's just not clear, how much the little bit more is, which actually works. So that's what we are trying to figure out at this moment. And yeah, that leaves me to thank you for listening. And of course, we have to give a big thanks to these people also, but we can probably say that one more time. Okay, I think this is it, right? Thank you.
You also want to thank all the attendees, so a big number that registered, and we had so very glad for you. Any question to the speaker?
Maybe I have a small question. In your formula that based on Witten formula on ADS, it reminds me a bit about the relation between trace and determinant in second quantization. Is it related to that?
Yeah, it is. I mean, you mean this formula? No, sorry, that was the wrong picture. This formula? You mean this formula, or I think the other formula?
The exponential or what?
Yeah, this is not the perfect strategy. Let me. This is later on. This year? Or I mean, the best one is
no, the other one that you refer to Witten.
Yes, this year.
Right. Right.
Yeah, this is related to trace and determinant. In particular cases, this is exactly right. I mean, in fact, I have seen versions of this formula used in your papers.
Okay.
Yeah, so it's. I mean, it simply has to do that, you know, start with a phenomenal algebra and you take this direct sum of these symmetric tensor products, right? And then if you take an operator T, you can define this gamma of T, which is somehow the direct sum of the tensors. And that operator, right? This procedure is, you know, this procedure is related to this. In some particular cases, this corresponds to what I've seen in your papers involving the determinant. So it's a little bit of a, I mean, it's related. It's not, not totally obvious, but it definitely, the answer is it related? Yes. And then one has to look at the details. Yeah.
Okay. Thank you. It's nice talk.
Okay, so can I ask the organizers to unmute us all so that we can clap for them? Because I cannot, right? I mean, that would be fantastic.
We can only mute, not unmute. That's
Okay. So, okay, then shall I clap for the organizers as a representative of the rest of the group? Because it has to be done. Okay. Thanks a lot for this lovely conference.
Bye to everybody.
Thank you all for joining.
Thank you.
Thank you.
Thanks for organizing this. Bye.
Thank you to you and to everybody. Very nice. Bye. And let's hope to meet in person now. Okay. Bye.
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 Ciao.
Ciao.